Welcome to the lecture series on numerical methods, finite difference approach. In the last lecture, I have discussed about finite difference approximations based on Taylor series approximation and Picard's method. So in this lecture, I will just go for numerical methods based on this Euler's method and modified Euler's method, and then we will just go for Runge-Kutta method. So in the last lecture, I have just discussed that whenever we will have higher order differential equations with the initial conditions, then we can just reduce all the higher order differential equations into the set of linear differential equations. So if it is order 1 equations are existing, then we can just use either this Picard's method or the Taylor series expansion. Then we are just proceeding in a form that once we are just we will have Picard's method, then we will just try to improve that method, that is in the form of Euler's method. And once it is a Euler's method we have, then we will just go for some higher order methods, that is in the order of order 2, that is as Euler's method here. Then to improve this Euler's method, again we will just go for this modified Euler's method. Then the improved form of this modified Euler's method is nothing but the Runge-Kutta method here. So if you just go for this Euler's method here, so the same problem we can just consider, that as if you just see here dy by dx, that is nothing but f of xy, and your initial condition that is given as y of x0 equals to y0 here. So if the initial condition is written in this form here, then first we will just go for a graphical approach, that if a curve is given, so at certain points we will have this differential representation. This means that this is just satisfied, or this differential equation is given at the point x0 and y0. So if this differential equation is provided at certain point, then at that point it can just form a slope with the tangent line, and if the tangent line is forming at that point, then based on that we can just derive this Euler's formula. So in order to achieve this formula, if you will just go for a true solution here, true solution means we can just distinguish these solutions in two forms. One, it is called a true solution, which is based on these numerical methods. Another one, it is called analytical solution or the exact solution, which can be obtained by using any of these real analysis methods. This is specifically called numerical analysis, that is called real analysis methods. So to obtain this true solution at y equals to f of x, since dy by dx is provided at the point x0 and y0 there, if you will just set off these coordinates here, that is in the form of x0, x0 means at this point we can just put this point as x0 here, and corresponding to this we will have a y0 point here, and at that point only we have this dy by dx slope can be formed with a tangent. So especially if you will just consider y equals to f of x is the true solution, and the exact value of y at x equals to x1, suppose on that curve if you will just consider as q here, that is nothing but y1 value here. So corresponding to y1 we will have a improvement in x1 also, that is nothing but we can just consider as x0 plus h here, that is nothing but x1. So h means that is nothing but the space length from here to here there. So x0 to x1, the space length is h we have considered, and if you will just consider this Euler's method to approximate this value at y at x equals to x1 here, we can just assume dy by dx is provided as f of x0 and y0, which is the slope of the tangent PR. If you just see, this is the tangent forming at the point x0 and y0, which is just intercepting this line qn, that is nothing but the next functional value with the corresponding x1 value there over. So if you will just take this f of x0 and y0, that is nothing but tan theta, since it forms the slope here. So tan theta is nothing but we can just say that this is, if this is p, this is b here, so tan theta is nothing but p by b here. And if you will just define this Rs here, that is nothing but we can just write h tan theta here. tan theta, especially we are just considering slope means tan theta there over. So that's why we are just writing f of x0 and y0, this equals to tan theta here. So then rs equals to h tan theta, then we can just define the total distance from here to here Rn, that is nothing but Sn plus h tan theta. So Sn means we can just consider Sn is nothing but y0 distance from here. So we can just write this one as like the next immediate value, that is a Rn. If you will just see here, Rn can be added with like a QR here. So then we can just find the total distance, that is nothing but Qn here. So if you will just write Rn here, Rn can be written as like Sn plus h tan theta here. So h tan theta means we can just say that y1 can be written in the form of y0 plus h f of x0 and y0 here. And the error associated with this value, that is given by QR, which is given by r equals to h square by 2 factorial f dash of zeta here. Since if you will just look at this picture here, the error means we can just say that the improvement that is just taken from y0 to y1 there over. So for that, if you will just consider this difference here, that is nothing but h square by 2 factorial f dash zeta here. So the general formula of this Euler's formula is can be written as like yn plus 1, this equals to yn plus h f of xn and yn here. Since the beginning, if we are just approximating this formula as in the form of like y1 equals to y0 plus h f of x0 y0, that is nothing but the y1 improvement. If you will just consider from this line here, that is nothing but this error term, it is just in a large sense we can just consider. And afterwards, if you will just consider this error term, again one more slope we have to consider, which can reduce the error term there over. That is why if we are just considering this higher order terms here, that is as 1 in the first sense, it is written in the form of y0 plus h f of x0 and y0 here. And the second one, we can just write this one as y2, this is nothing but y1 plus h f of x1 y1 here. Similarly, if you will just proceed, then in the nth form we can just write this one as yn plus 1, this is nothing but yn plus h f of xn yn here, with the error term r equals to h square by 2 factorial f dash of zeta n y. Since this error term always represented in the first order differential equation form here, where zeta n should be lies between xn to xn plus 1. Since whenever the slope is increasing from point to point, this error is getting reduced, and this error lies between this immediate below point to the next approximated value. So that is why in the beginning I have just told that this error for this Euler's formula is of order of h square, or the second order approximation we are just getting for the error terms. And if you will just go for a practical example here, that is based on Euler's method here. Suppose the question is given like using Euler's method, compute y1 and y2 taking h equals to 0.1 from the following differential equation, that is as dy by dx equals to 1 plus xy square, y0 equals to 1 here. Also compute the error term there. So if you will just go for this equation here, especially we can just write this equation as dy by dx, that is nothing but your f of xy here, which is represented in the form of 1 plus xy square, and y0 is provided as 1 here. So that is why we can just write y dash as f of xy, that is nothing but 1 plus xy square, and y double dash we can just express, this is nothing but f dash of xy, this is nothing but we can just write y square plus 2xy 1 plus xy square here. Since already we have explained that one f dash of xy is nothing but we can just write it as fx plus fy into f here. So that is why I have just written in this form here. So then especially for x equals to 0.1 here, we can just write y1 equals to y0 plus h f of x0 y0 here. So if you will just write in this form, since every value it is known to us, y0 equals to 1 here, x0 equals to 0 here. So, if I will just use these values, then I can just write this one as y1, this can be written as like 1 plus h is nothing but it is just specified as like 0.1. So, that is why 0.1 into your f of xy value, that is nothing but I can just write as like 1 plus x0 y0 square here. So, if I will just do this one like the final form of this one 1 plus 0.1 into 1 here, that is nothing but 1.1. So, in the error term, if you will just go for this computation, so epsilon 1 this can be written as like half h square like y double dash of zeta here, since f dash zeta it is just written in the formulation. So, that is why it is written as a half h square y double dash of zeta. This can be written as half of like h square f dash of zeta y, where zeta should be lies between like 0 to 0.1 here, and especially I can just write 0.5 into 0.01 into 1.45662 here, since f dash of zeta y, if you will just see, this is nothing but 1.45662 here at x equals to 0. So, that is why this final value it will just achieve as 0.00728. So, that is why this final solution we are just obtaining, that is in the order of h square. If you will just see 0.00728, it is just represents that value corresponding to h equals to 0.1 here. So, then for x equals to 0.2, if you will just use this formula recursively, then again we can just write this formula as y2 equals to y1 plus h f of x1 y1 here. So, if you will just put the value here, that as y2 equals to, we can just write y2 equals to y1 plus h f of x1 y1 here. So, that is why y1 is just if you will just see the value here, that is just given as 1.1 here over. So, that is why 1.1 plus h, that is nothing but 0.1 here, into your values, that is as a functional value, that is like 1 plus xy square here. 1 plus xy square means we can just write as x plus y square means 1.1 it is just giving. So, final value we can just write that as 1.2121 here. So, maximum truncation error or error propagated from first step plus the local truncation error, that is we can just write as epsilon 2 equals to epsilon 1 into 1 plus h fy of x1 y1 here, since this error this is associated with the second approximation here. So, that is why we can just consider plus half of h square f dash of zeta y plus the local error that has been associated or already it is associated there over, this is the error term here. So, in the complete form, if you will just write this total error here, this error can be written as epsilon 1 into 1 plus this h is there. So, fy of x1 y1, that is nothing but 2h x1 y1 plus half h square into y square plus 2xy into 1 plus xy square here. So, if you will just put all these values, h equals to 0.1 and x1 is can be written as in the form of 0.1 also there, and y1 it is just the computed value, that is as 1.1. If you will just see, this y1 value is coming as 1.1 here. So, that is why it can be written as like 0.00728 into 1.022 plus 0.005 into 1 plus 1.4692 plus 0.6272 here, and the final answer just it is just giving you 0.0179. If you will just see this previous step error, so this error is just given as a 0.00728, and in the next step this error is reduced to like 0.0179 here. So, whenever we will just go for like higher steps, then the error will be minimized afterwards. So, then we will just go for like a modified or improved Euler's method. So in the Euler's method especially we are just using only this first step values, that is like y1 equals to y0 plus h f of x0 y0 there. And in the modified Euler's form we can just take the average of like a previous step calculation into the plus the next step calculation, and it can be, since we are just taking the average values of these two, we can just modified form we can just write this formula as y1 equals to y0 plus h by 2 into f of x0 y0 plus f of x1 and y1 there. Since two unknowns are associated in this formula here, if you just see two formulas are also associated here, so that is why we can just consider this y1 star, it can be computed from the earlier step by using only Euler's method there. So Euler's method especially it is written as y1 equals to y0 plus h f of x0 y0. So that is why from this we can just calculate this y1 star at the beginning of the problem. Then successively we can just put these values in this formulation here, and if you will just see in a fundamental way also, this can improve the nature of this approximation compared to the earlier one. So that is why I have just written this statement, the Euler's method is given by like yn plus 1 equals to yn plus h f of xn yn here, having the error of order of h square here, second order. And the modified Euler's method is an improvement over the earlier method, giving the error in the order of hq here. And in this method especially y1 can be obtained by using the earlier Euler's method, and it can be improved by taking the average value of the gradients of f of x0 y0 and f of x1 y1 star. Since y1 is unknown to us, that is why we are just using this earlier Euler's method to get the value of y1 in a improved form or in a modified form. So then if you will just take k as h of f of x0 y0, then we can just write this one as, or in the modified form y1 can be written as y1 equals to y0 plus h by 2 f of x0 y0 plus f of x0 plus h, that is nothing but x1 here, and then y1 star which can be written as like y0 plus h f of x0 y0, since already we have defined here that is as k1 here, k1 is nothing but h f of x0 y0 which can be written as y0 plus k1 here. So for the further improvement, if you will just go for the error in the modified Euler's method, to show this error, if you will just expand this Taylor series as y1 equals to y0 plus h by 2 f of x0 y0 plus h by 2, if you will just take the next term, that is as f of x0 y0 plus h del f by del x plus k del f by del y plus half h square del square f by del x square plus 2hk del square f by del x del y plus k square del square f by del y square plus all other terms. Especially we are just taking this one as in the form y1 equals to y0 plus h by 2 f of x0 y0 plus h by 2 f of x1 y1 there itself. So that is why we are just considering, since x1 can be written in the form of like x0 plus h and y1 can be written in the form of y0 plus kh there. So that is why it can be expanded in Taylor series form, and in the, if you will just expand all the terms, then this is the combined form of this all the terms here. If you will just use like k equals to suppose h f of x0 y0 here, then we can just get this series as y1 equals to y0 plus hf by 2 plus h by 2, if you will just see, then f plus h into del f by del x. Since k is replaced by here h f of x0 y0, so h can be taken common, so f can be multiplied with this term, so it can be written in a compact form here. So similarly, if in this term also, if you will just replace k by h f of x0 y0, so it can be represented as a 2hf del square f by del x del y plus h f square del square f by del y square here. And in the final form, if you will just see, so this can be written as y0 plus hf plus, if we will just take common from all other terms, that is if you will just see here h del f by del x here plus hf del f by del y here. So if you will just write in a compact form, that is if you will just take like h f by 2 and add it off, then we can just write this one as, or if you will just subtract this hf by 2 from both these terms, this can be represented as hf plus h square by 2 del f by del x plus f del f by del y. So, remaining terms are there. So, only we are just adding hf by 2 term here, subtracting from this one, or you can just consider this addition of these two terms can be represented in this form here. So, now if we want to find the exact solution, that is y of x0 plus h, that is nothing but y of x1. So, if you will just take the Taylor series expansion, so directly we can just obtain this Taylor series expansion as y of x0 plus h. So, which can be written as y0 plus h y0 dash plus h square by 2 y0 double dash plus h k by 3 factorial y0 triple dash. And if you will just subtract like from the earlier formulation here, y1 is there and this is y of x1 is here. If you will just take the difference, then we can just find that this term is 0, this term is 0, this term is 0 here. And we can just obtain a subtracted term that is in the form of minus h cube by 2l del square f by del x square plus 2f del square f by del x del y plus f square del square f by del y square plus 2 del f by del y into y double dash here. That is nothing but order of h cube. So, we are just finding this improved form of this like Euler's method if we are just going for like higher approximations. So, in the earlier method we have just obtained this error is of order of h square, here we are just obtaining this error is of order of h cube here. If you will just go for a practical example, that is specifically if it is written in the form of like dy by dx equals to x minus y and y0 equals to 1 here, for x equals to starting point is like x naught equals to 0.2 and it is incremented by 0.2 and last point is 0.4 here. So, that is why it is just written as like x naught equals to 0.2 incremented by 0.2 here. So, that is why we can just consider like x1, this can be written as 0.2 plus 0.2, that is nothing but 0.4 here. So, initial value x0 is 0.2 and x1 is like 0.4. So, two step calculation we have to move here. So, for x equals to 0.2 here, if I will just write the increment here, increment means I am just writing h equals to 0 point here. So, that is why x0 if initial value if you will just consider here, that is as y of 0 is 1 here, especially we can just write x0 equals to 0 and y0 equals to 1, then the first improvements if you will just consider here, that is first improvements if you will just consider here, that is like y0 as 1, then we have to find y1 here and x0 is given 0 here, then x1 is given as x0 plus h here, that is nothing but 0 plus 0.2, that is nothing but 0.2 here. So, based on this we will just find first y1 star here. So, for y1 star if you will just consider like y0 plus h f of x0 y0 here, then y0 is given as a 1, especially I am just putting here, then h is given as a 0.2 here, then the formula that is as x0 minus y0 here. So, x0 is 0 here minus y0 is 1 here. So, if I will just take the total sum of the term here, so that is just giving you 0.8 here. So, the immediate improvement if we want to find, since y1 star we can just write, this is the calculation from Euler's method only, original Euler's method. And then if we want to find a modified form or a improved form of this Euler's method, then y1 can be written as y0 plus h by 2 f of x0 y0 plus f of x1 y1 star here. So, y0 is given as 1 here, then h is 0.2 by 2, then f of x0 y0 it is just obtained as like if you will just see here, that is x0 minus y0 here, that is a minus 1, then plus we can just write h by 2 0.2 by 2 here. So, like f of x1 y1 star here. So, y1 star it is just computed as 0.8 here. So, if I will just put x1 as a 0.2 minus 0.8 here. So, final answer it is just coming as a 0.84 here. For x equals to 0.4, that is we can just consider x1 as a 0.2 here, then x2 equals to 0.2 plus 0.2, that is nothing but 0.4 here. So at y at 0.4 especially, we can just say this one. This can be obtained if you will just first compute y2 star. Y2 star can be written as y1 plus h f of x1 y1 here, that is y1 can be written as 0.84 plus 0.2 into 0.2 minus 0.84, and the value is coming as 0.712, and specifically based on this y2 star value we can just compute y2 here. So y2 can be written as y1 plus h by 2 f of x1 y1 plus f of x2 y2 star here. So if you will put the y1 value, that is nothing but 0.84 here, so h is 0.2 by 2 here, then f of x1 y1, that is nothing but minus 0.64 plus 0.4 minus 0.712 here, and the final value it is just obtaining as 0.7448 here. So analytic solution it can be obtained if you will just take the direct integration of this differential equation, and the value can be obtained as like x minus 1 plus 2 e to the power minus x here. And if we want to compute the value at 0.2, so specifically if you will just put here like x equals to 0.2, then the value is given as 0.8375 here, and for 0.4 the value is given as 0.7406, and if you will take this difference between these two values, then we can just find the error in that method. Then we will just go for like a Runge-Kutta method here. Runge-Kutta method is nothing but the improvement of modified Euler's method. If you will just see here, we are just considering different terms as in the form of like k1 as a function of like h f of x0 y0, k2 as f of x0 plus h by 2, y0 plus k1 by 2. This is nothing but the improvement of like k1 term in this term here. Then again we will just take a improvement of k2 term in the next term here. Then again we will just consider a next improvement of the previous term in the next term there itself. If we will just take the combination of all the terms here, then we can just obtain the final improvement of this term here. So improvement can be added with this initial condition to get this final solution of this problem here. So if you will just go for a practical example based on this Runge-Kutta method, we can just write here dy by dx equals to y minus x, and y of 0 is 1.5 here. So especially we can just write this initial condition x naught equals to 0 and y 0 equals to 1.5 here, and we have to compute these values, that is as like x1 equals to 0 plus 0.2 improvement, that is 0.2 here, and x2 equals to 0.2 plus 0.2, that is nothing but 0.4 here, x3 is nothing but 0.4 plus 0.2, that is nothing but 0.6 here. So since the value is asked to compute up to 0.4 here, so we have to compute these values at like x0, x1 and x2 here. So first x0 value it has been given to us. So x0 is written as like 0 here. For h equals to 0.2, x0 equals to 0 and y0 equals to 1.5, we can just use k1 equals to h f of x0 y0 here. So 0.2 into 1.5 minus 0, that is nothing but 0.3 here. K2 equals to h f of x0 plus h by 2, y0 plus k1 by 2 here. So that's why this value is just given as 0.31 here. Then again for computation of k3, if you will just consider these values as like h f of x0 plus h by 2, y0 plus k2 by 2, then we can just write this value as 0.311. Then further improvement, if you will just implement this k3 value in k4, then we can just find the value as 0.3222 here. So final, after combining all the 4 terms here, the final improvement is obtained as 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4 here, and the value is obtained as 0.3107 here. So y1 can be written as y0 plus k, that is nothing but we can just write 1.8107 here. Then for the further improvement of this Runge-Kutta method, systematically we will just use all other values like x2 equals to 0.4 if we want to find, then we can just implement here x1 value and y1 value for the further improvement of k1, k2, k3 and k4. Finally, we can just obtain y2 as 2.14587 here. Thank you for listening this lecture.